Okay, welcome to week 5. We are going to look at section 6.1 in this video. I apologize in advance if this one goes a little bit long. It really isn't that heavy as far as things go, but the calculations take a little bit of time, and so it's possible this could take longer than expected. So we're going to look at the distinguishing between discrete and continuous random variables. We've already looked at discrete and continuous before, so the beginning will be a little bit of review. We're going to identify discrete probability distributions, graphing discrete probability distributions. I'm not going to make you do them by hand, but I want you to see what it looks like. Compute and interpret mean of a discrete random variable as well as the standard deviation of a discrete random variable. Plus, you're going to interpret the mean of the discrete random variable as an expected value. So the expected value and mean are the same thing, but I will talk about what that is in a minute. So one thing I need to point out is that you're going to come across several different ways to calculate mean and standard deviation depending on what you are doing. So make sure that in your notes you are clearly labeling what it is you are calculating the mean and the standard deviation of. And there will be keywords to look for. I'll point those out when I can, because it's really going to depend when you get to the test. You're going to have to look for certain words. Be like, oh, okay, so this is a discrete random variable, so this is how I calculate the mean. So there's going to be several different things you're going to learn, and there's going to have different ways to calculate the mean and the standard deviation. So let's just jump into it. So a random variable, we've already kind of talked about this. It's a numerical measure of an outcome from a probability experiment. So basically its value is determined by chance. Random variables we use the letter X. So something that would be a discrete random variable is when we are rolling a dice, the outcome of the roll of the dice. That would be, because it is random, it's by chance. Sorry. That would be a discrete random variable. That's a random variable. So a discrete random variable has a finite or countable number of values. So this, we've talked about discrete before. Discrete, when we graph it as points. We do not connect those points. You have to lift up your pencil or pen to get to each individual piece of data. So, but a discrete or a continuous random variable is when you don't lift up your pencil. All the values in between are also valid. So rolling a dice and the outcome of that would be discrete, because those are just counting numbers. Those are not, you can't get 1.5 when you roll a dice. A continuous random variable would be like how far you've traveled in your car. You can't get to 5 miles if you didn't do 4 1/3 miles. So all of the values in between 0 and 5, every single value, an infinite number of values have been reached. So that would be a solid line on the graph, whereas a discrete variable, you would not connect them with a line, because 1 and 2 are two different answers, but 1.5 is not a possibility. Okay, let's move on. So we're going to be looking at these 3 things, and you're going to decide if they are continuous or discrete. So think about it. If you need to think about it for a second and pause, go for it. So how about the number of light bulbs that burn out in a room of 10 light bulbs in the next year? So this would be a random variable. Is it discrete or is it continuous? You're right, it is discrete, because 5 light bulbs can burn out, but 5.3 light bulbs cannot burn out. So the number of leaves on a randomly selected oak tree. Now I guess you could probably make an argument for continuous, but this is discrete. The reason I say you might be able to make an argument for continuous is because if you're counting the leaves as they grow as not a complete leaf, so maybe when it first sprouts, it's 0.1, and then as it grows, but we're not really talking about the size. We're really talking about countable numbers. Now it may have thousands and thousands of leaves, but they're still countable. You still would not have a continuous line on a graph. How about the length of time between 911 calls? That would be continuous, because as the time is basically always continuous, unless you're talking about the way you get paid. If you get paid in 15-minute increments or the nearest 15 minutes, like a lot of employers, if you clock in at 5:05 or clock out at 5:05, you're paid till 5. If you clock out at 5:08, you're paid till 5:15. Things like that happen. However, length of time between 911 calls, you're not going to get 5 minutes without hitting 4 minutes and 35 seconds. So it is a continuous. You would draw a line on your graph rather than individual points. Okay, let's move on. A probability distribution provides the possible values of the random variable x and the corresponding probabilities. A probability distribution can be in form of a table or a graph or a mathematical formula. So tables are what we're going to look at the most here in the beginning. It is a probability distribution, looks really similar to a relative frequency table. They look really similar, and they're calculated, the probabilities are calculated the same way. So let me show you right here. So this is a discrete probability distribution. So it recommends the number of movies streamed on Netflix each month. So take a look over here. I don't know how many people were polled. I don't know any of that stuff, but it says that 0.58 is 58% probability of that a person randomly chosen has streamed one movie during the month. So this is calculated the exact same way that frequency distribution is calculated, but almost all of the problems here, you're going to be given the probability. So you're not going to be calculating probabilities, you're going to be using the probability given. So the right column is the probability of that happening. The left column is your random discrete variable. And I guess technically, you can watch 1 1/3 video or 1.45 videos because, sometimes we don't like one and so we turn it off. But I believe that Netflix would still count it as a whole movie. It sure does in your continue watching. But so they would count them in whole movies, but whether or not you watched the whole thing. I believe it's probably number of movies started is how they would look at it. Okay, so let's move on. So here's the rules for our discrete probability distribution. This is the same thing as what we did for our relative frequency table. So this is really, our notation is ugly. This right here is summation notation. So this is saying the sum of all of the probabilities in the probability distribution will equal 1. So the sum of the probabilities, I can't write and talk at the same time, equals 1. So, of course, due to rounding, your probability distribution might be slightly off. But if I give you a table and I say, is this a probability distribution? They will add to exactly 1. I will not give you one that has been rounded. It will add to exactly 1 or it won't add to 1. If it doesn't add up to 1, it's not a probability distribution and not a discrete probability distribution. So this is the same thing as with our frequency tables, our relative frequency tables, Our probabilities, each probability is going to be between 0 and 1 inclusive. So it can be 0, it can be 1, and it can be any number in between there. It will not be higher than 1 and it will not be less than 0. So these are the two rules for our discrete probability distribution. Let's move on. So probability histogram. It's a histogram where the horizontal axis or the x-axis is the value of the random variable. The vertical axis or the y-axis represents the probability of that value of the random variable. This is the same thing as a relative frequency histogram. So I'm going to show you that with the Netflix results what that histogram would look like. So down along the bottom I have these each are the numbers of movies streamed during the month, and then our y-axis is the probability. This is the same thing as the relative frequency histogram, except for instead of relative frequency, it says probability. All right. So suppose we ask a basketball player to shoot 3 free throws. We let the random variable x represent the number of shots made so that x is 0, 1, 2, or 3. The table shows a probability distribution for the random variable x. We're going to graph that probability distribution given in the table. I'm going to show you another way to do a probability histogram. But this only works for discrete, so a discrete probability histogram. If it was continuous, it's going to look different. Because this is discrete and because it's not continuous, the values do not bump up against each other. This is a much simpler way to draw a histogram. You just draw a line up and you put the dot at the top, at the very top of your line. This is just an easier way to draw it. It's exactly the same meaning as that other histogram that I showed you. Either one is absolutely correct. You may run into either one of them on your homework, in the book, on a test. You could run into either one of them. Or if you have take-home homework, we do have an assignment coming up that's a take-home assignment. If that's the case, then you can draw them this way. Sorry. Next, we're going to talk about the mean of the discrete random variable. So we're going to compute the mean of the probability distribution for the right, which represents the number of DVDs a person rents from a video store during a single visit. This should not be rents from a video store. I thought I changed this. This should say, this is the streams, number of movies, streams from Netflix. And number of movies a person streams from Netflix during the month. I thought I fixed this. Sorry about that. I'll try to fix it before I upload it to, I'll try to fix the PowerPoint before I upload it to my Open Math. Okay, so we're going to compute the mean. So we can't just take all of the values and find the mean of those values. We can't just add 0, 1, 2, 3, 4, and 5 because the probability of each of them happening is different. This is similar to when we had the frequency over here. So remember when we had the frequency, and if this was 1, 4, 8, 12, 3, 2, because these frequencies are different, they hold higher values, so I would have had to multiply 3 times 12 plus 2 times 8 plus 1 times 4 and figure out how many there were. This is really similar to that. And I made a big old mess. Let me clean that up. Okay, so what we have to do is you take, this is our formula right here. You take the x, this is the x, and you multiply it by the probability. You do that with the next one. You take this x and multiply it by that probability. You're going to take each one, so this is x times that probability of x. And then this is the next x times that probability of x, and you do that with each one of them all the way through. So this is each x times each probability of that x happening, and then add them all together, and that will give you your mean. That gives you the mean of that. Sorry about that. That gives you that mean. So the mean of this is 1.49. So what's this? Okay, so that means that the average number of movies that people stream every month based on this, the average number of movies is 1.49. That's what this means. That's what the mean of this discrete random variable means. So suppose an experiment is repeated n independent times. So that n could be any number. The value of the random variable x is recorded. So as we repeat the experiment n times, so let's say I'm flipping a coin. I flip a coin, let's say 10,000 times, and I record how many times I got heads. So as the number of experiments increase, the mean value of the trials will approach the actual mean. So the actual population mean. So that mean of that random variable x. So for example, you know that the probability of a flipped coin landing on heads is 50%. As I flip the coin over and over and over again, the more I flip the coin, the closer and closer the number of heads that I've flipped will get to that expected value, will come to that mean. That will get closer and closer. So as I keep flipping the heads, this is called the law of large numbers. Saying as my X, or as my number of trials, as the number of times I flip that coin gets larger and larger, I'm going to get closer and closer to the mean. So as we test more and more people and how many videos that they watch every month on Netflix, or that's not just videos but movies, as we pull more and more people, we're going to get closer and closer to that 1.49 average. It doesn't mean if I test 5 people, I'm probably not going to get 1.49. But if I do 5,000 people, I'm probably going to be pretty close. If I do 100,000 people, I'm going to be really close. The larger the number of people I sample, the closer and closer we're going to get to mean. That's what all of this means, and that's what it means to interpret the mean in this case. So let's move on. So here's a kind of visual of it with the Netflix right here. So here is our 1.49. Well, that's about 1.49 right there. So trial 0, we're far from it. Trial 50, we're getting closer and closer. Trial 100, look, we're pretty much right at it. And this is, once again, the law of large numbers. So let's move on. So because of the mean of the random variable is what we would expect to happen, we call it the expected value. We call that mean the expected value because as the number of trials increases, we expect it to get closer and closer to that. So that's why we call it the expected value. If I use the word mean or I use the word expected value, I'm talking about the same thing. If I say the mean of the discrete random variable x or the expected value of x, that means the exact same thing, and we're going to use the same calculation. So this did some weird stuff on me. So we're going to talk about this. So the probability, so a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old woman for $530. According to the National Vital Statistics Report, the probability that she will survive the year is 0.99791. We need to compute the expected value of this policy to the insurance company. So basically what this is saying is how much money are they making off of these policies? How much do they expect to make off of all of the policies that they've made to a 49-year-old woman? How much is it worth to them? So if the woman survives, so this is one woman, if she survives, the company gets that $530. And so there's a 0.99791% chance, or 99.791% chance, or 0.99791 probability that they will get that $530 and not have to pay anything out. So what if she doesn't survive? If she doesn't survive, she still paid in that $530, but then they had to pay out that $250,000. They had to pay that out, so that net is negative $249,470. That is the net on that policy. So, I mean, they lost $249,470 on that woman. But there's only a 0.00209 probability that she will die that year, that one woman will die that year. But think about it. They've sold these policies to a lot of 49-year-old women. So you think if we calculate the mean on this, calculate that expected value over all of the 49-year-old women that they've sold this policy to, how much basically are they making off of each policy? How much does it average out to that they make off of each policy? So let me show you how we do this. So I'm going to take the expected value of x, and as we did before, we take the mean. We're calculating the mean. I'm having issues. So they take 530, and I just lost it. Okay. times the probability. So this is $530 times the probability they're going to make that just that $530 plus negative 249,470 times that probability, which is, I'm going to put it in a different color so it shows up, 0.00209. So we have the negative 249,470 times the probability that they're going to lose that negative 249,470. So that comes to $7.50. So basically, with all of the 49-year-old women that they're going to sell this to, they expect that they will make $7.50 off of each policy. So that's still a profit. So there are people called actuaries, that this is their job. They actually do this kind of math to assess the value of different policies and try to figure out what is a good price point so that they're going to sell enough policies to get to this mean, so that they're not pricing it too high. So they don't want to price it too high that nobody buys it. And then they don't want to price it too low that they're not going to make any money. So $7.50 may not seem like very much, but if they sell a lot of these policies, it's at $7.50 per policy. And then, of course, you have people who are 25, 30 years old that are also buying life insurance policies, and I bet you the company's making a lot more money off of them than they are off of these 49-year-old women. All right. So let's go do another one. Let's see here. Where am I? I'm having issues. Okay. So we already computed that expected value, did we? We already computed that expected value, didn't we? Let me see here. Yeah, we did. So I'm having issues. Okay, we already computed the expected value for the Netflix. So I would like you to try this one. So I would like you to compute the expected value for the number of free throws made by a group of basketball players asked to shoot 3 free throws. So here is my probability distribution. I would like you to use that formula that we just used and see if you can compute that expected value. Once you have done that, come on back and we will go over it together. So take a moment, pause, and then we will come back and we will talk about it. All right. Hopefully you did that on your own. Hopefully that worked out for you. So let's take a look at this. So we are going to compute this expected value. So we will do, so the expected value of x, it's 0 times 0.01 plus 1 times 0.10 plus 2 times 0.38 plus 3 times 0.51. So you do all of that math, add them all together. You should have gotten 2.39. That would be the expected value. So if the basketball players, I'm not sure who these people are because that's a pretty good free throw average. If they keep doing it over and over and over and over again, we're expecting them to make an average of 2.39 free throws out of 3. And I'm sure you can think about exactly what type of situation this would be good, what type of situation this math would be good for computing, why we would like to know how many we would expect them to make. I'm sure you can figure that out. All right, so let's move on. Let's talk about standard deviation. I know this is your favorite topic in the world, standard deviation. So let's talk about standard deviation. So this looks daunting, but I'm going to break it down into small pieces. So essentially what we do is we take x, which is the value, like say, number of videos rented, minus the mu of x. This is your expected value. The mu of x is your expected value. Square it, multiply it by the probability of the thing happening, and then you add all of those together. Once you do all of that, you take the square root. So we're going to talk about this in a second, and I'm hoping that you'll be able to see exactly how we do this. I'm going to go to the Netflix data. So we remember that the expected value or the mean of the Netflix data was 1.49. So we're going to calculate the standard deviation. It says to calculate the variance also. I don't know if you remembered me talking about the variance. Variance is something I've never used in any practical way. However, every stats class and book I've ever encountered asks for the variance. All the variance is the standard deviation before you take the square root. Before you take the square root, it is the variance. Once you take the square root, it is the standard deviation. So let's go there. All right, so remember, okay, our mu of x is 1.49. So I took 0, I subtracted 1.49, so it's there. Then I square it. Once I square what I got here, and then multiplied it by the probability. So negative 1.49 squared is 2.201. Multiply it by the probability, I get 0.133206. So I took 1, I subtracted 1.49, I got negative 0.49. I square this number, I got 0.2401, multiplied that by the probability, which is 0.58, and got 0.139258. Did that same math through all of these. You can see it's x minus mu, then square it, multiply it by the probability, then I add all of these together, and I got that. Once I added all of these probabilities together, got 1.384898. This is your variance. That's what that is. That is the variance. So now I'm going to take the square root in order to get the standard deviation of x. That's what this is right here. It's the standard deviation. That little sub x means it is of your discrete random variable. Took the square root. My standard deviation is 1.1768. So what we can do with these two numbers now is we can use these to calculate if something is unusual or not. So since I know my mean is 1.49, what if I pulled a simple random sample? I called somebody on the phone and said, how many Netflix movies did you stream last month? And they said 5. So I could take my mean plus 2 times 1.1768 and figure out whether or not that would be an outlier. 2 times 1.1768. So, I did something weird here. So 1.49 times 2 times 1.1768. So that is 3.506. So any number larger than 3.506 is an outlier because it's 2 standard deviations away from that mean. So if somebody watches 5 movies, then that is definitely an outlier. I'm hoping that made sense. I'm going to show you other ways, and we're going to look at other things after this. Okay, so now I would like you to compute the standard deviation of this probability distribution for the free throws made by a group of basketball players. So I would like you to take this data. I already set up on the next screen. I set up the chart for the math. You do not have to use mine if you don't like, but I set that up for you. And go ahead and do the math and pause this and see if you can calculate that standard deviation. Go ahead and see if you can do that and pause it and then come back and we'll do it together. All right, I hope you paused that. So I'm going to do all of this math. So remember, our mean of x was 2.39. So that was our mean or our expected value. So I'm just going to do the subtraction. So this one, negative 2.39. Once I square that, I get 5.7121. I multiply it by 0.01 at 0.057121. So take 1 minus 2.39. I get negative 1.39. Square that number. I get 1.9321. And then once I multiply this by that 0.1, I get 0.19321. So 2 minus 2.39 gives me negative 0.39. Square that number, 0.1521. Multiply this by the probability, get 0.057798. Now take 3 minus 2.39, you get 0.61. Square that number, 0.3721. Multiply this by that probability, get 0.189771. Once again, we have to add all of these together. That gives me 0.4979. That's your variance. That's the variance. So now, in order to get the standard deviation, you just take the square root of the variance, which gives me 0.7056. Beautiful. Good job. If you got 0.7056 right now, you should pat yourself on the back. So what if I said that I went out there, I'm one of these people, I'm one of these basketball stars, which if you saw me and how short I am, you would laugh, and I only hit one free throw. Or let's say one of these basketball guys went out there and he only hit 1 out of 3 free throws. Let's take a look at whether or not that is an outlier. So remember how we calculate the z-score. So I'm going to take the x, so 1 minus our mean, 2.39, then divide it by the standard deviation. So 1 minus 2.39 divided by 0.7056. My z-score is negative 1.97. Now this is not quite an outlier. It is not, because my z-score is not below negative 2. It's really close, but it's not below negative 2. It's not considered an outlier. Right, so that is the end of 6.1. Go ahead and do the homework. Send me an email or a message if you are confused and you need some help. Just let me know. Thank you.